It's a pleasure to have Sergei Gukov today from Caltech, and he's going to tell us about KK modes, resurgence, and compactification divisors.
Yeah, thank you so much. How many of you in the audience are comfortable with these words? Can I see show of hands? Okay, 3. Okay, that's good. I'm half joking. So the goal is to hopefully demystify some of these terms and see how they play together. So this talk, I prepared in a way that I didn't know if I should be too pedagogical or too technical, so it's somewhere in between. So feel free to ask questions because most likely I missed the mark anyway. More technical details could be found on some of these papers. I mean, it's largely based on this massive collaboration with these two gentlemen, Dupay and Poshan-Sin. But other papers are also quite relevant to other parts of the talk. And if I were to say, like, from the bird's point of view, what the talk is about, it's about strongly coupled quantum field theories. So this is something we don't understand systematically, meaning we have a limited set of tools, and I'll try to use as many as possible to bootstrap them, to shine light on some of the rather delicate phenomena. So that was part of the reason I tried to make it in some parts non-technical. But honestly, again, the phenomena I'll be talking about are rather delicate. So you may not wish to care about them. So that could be one walkout message of this talk, that, oh, this is like too pedantic for me. But some of us who love QFT and look for non-perturbative, strongly coupled definitions feel that this is kind of necessary step to understand such things. So my personal motivation on the subject is to understand kind of a case study, if you wish. There's a whole class of theories that string theorists love that obtained by reduction or compactification from high dimensional theories to low dimensionals. And for some of them, we don't have Lagrangian description, so we just give them a name, but it's a placeholder for something that's like on a to-do list that we should understand better. So this is going to be a specific class of theories. It's still huge. It's very large, called T of M. So M is some n-dimensional manifold. And if we start with 6 dimensions, where we believe we can have the largest dimension where we believe we can have quantum field theories without gravity, just on their own. So this talk will have nothing to say about gravity, although many questions about metric, Riemannian geometry will naturally come in. So if we start there in 6 dimensions and put this theory on n-dimensional manifold, we can ask, what does the physics in 6 minus n dimensions look like? This is a very standard question. String theorists ask it starting in dimension 10 or 11, and then compactifying on Calabi-Yaos and hoping that electrons and muons pop up as effective description. So this is a very standard paradigm. In fact, it goes all the way back to Kaluza and Klein. So KK in the title represents Kaluza and Klein. And we'll be asking the same question here, like, what does the physics of these theories look like? So for example, if I take 4 manifolds, which is a very mysterious mathematically world, and compactify 6-dimensional theory on a 4 manifold, we get something 2-dimensional. If we compactify 6D theory on a 3 manifold, we get some 3-dimensional theory. And this resulting theories live in dimensions like 2 and 3, and we compactify in a second on a 2 manifold, and that's going to be 4. So these are resulting theories in dimension that we usually kind of study. So it's not too far-fetched. It's actually very close to many of the tools we use and should know. The only problem is that in many cases, we don't know how to write Lagrangian for these theories. And that's the issue. So if we did, I didn't have to give any of this talk or any part of this talk. So the challenge is that, to me, this is not necessarily the end of the story, just a particular class where we can use some of the tools I'll describe to you as a stress test. But if you have other systems, such as quantum phases in condensed matter or other strongly coupled systems, we can pay attention and basically transfer many of the techniques or methods or questions I'll be asking into those systems. So that's the idea. And again, feel free to ask questions at any point. So The definition, technical definition of this T of M is that we'll start with a maximally symmetric, which means also supersymmetric theory in 6 dimensions, and just reduce it on a manifold of dimension M. Okay. So for many purposes today, it will suffice to consider just a billion theory. So this 6D theory is classified by something like a choice of gauge group, and we can take either a single gauge group, U1 gauge group, which corresponds to single fibrane in the language of string theory, or simplest non-abelian one, which is SU2. So SU2, for many purposes, if you think about gauge invariant objects, behaves very much like U1, except that in many cases, it's almost like U1, but you have to quotient by Z2 Weyl symmetry. And you'll see this later in the talk. And just like this dot 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 stands for various choices, that includes some of this gauge group. When we are in doubt, we can always ask for simplest types of manifolds. We don't have to worry maybe in the beginning about exotic smooth structures and things like that. We can just take something very familiar, such as circle cross a 2-sphere, products of spheres or 3 torus, something that's fairly intuitive and easy. And already in this sort of simplest instances of gauge group and choice of manifold, we'll see that interesting questions arise, and we'll use them again as a stress test, as a case study for delicate phenomena. Okay. So as we go through this journey, especially for the first part of the talk, so what I'll try to do, I'll try to basically walk us through this sort of Kaluza-Klein reduction or compactification, and just see what we get. We'll see some inconsistencies, we'll see ways to fix them, and some of them will lead to surprises. I know when the result is surprising or something is unexpected, it's natural to like frown and then be skeptical about it, but we can always fall back on the basic case of this U1 story, which corresponds to taking a single fibrane and its whole volume theory and just wrapping it on some manifold. And there, in some sense, we have no excuse, because even the starting point is already strongly coupled, non-Lagrangian in general, but at least for this special case of gauge group U1 or single fibrane, it's a free theory. So there are no interactions. So we should be able to follow exactly what Kaluza and Klein did 100 years ago and write down the resulting theory. So if there are no interactions, there is nothing to worry about it. We just have to carefully do the bookkeeping, decompose everything into, I don't know, spherical harmonics or their analogs on this MNs, and that's it. That should be the result. And for this, it's useful to know that the spectrum of such theory in 6 dimensions, the starting point is 2-form field B. So that's rank 2 or 2-form tensor. It's self-dual, so that's usually imposed as equation of motion. That's the only reason that the theory is non-Lagrangian. In fact, it's kind of mildly non-Lagrangian. The rest is totally normal. So we have 5 usual scalars. If you think about fibrane, they can correspond to normal directions, orthogonal directions to fibrane world volume. So 6D is the world volume theory of the fibrane. 5 directions parametrized by the scalars are like normal directions. So 6 plus 5 is 11. So fibrane lives in 11-dimensional M theory. That's part of the reason. And then the theory also has fermions, which transform in 4 of SO6, or rather SP, and 4 of SO5 internal symmetry. So there are 16 of them, 4 times 4, and that's basically the spectrum of the theory. All of the fields are free. Nothing's interacting. So when we in doubt, we can just always fall back on this case and ask, okay, what happens here? And we'll do it number of times. And again, the reason I choose SU2 is because in practice, the answers for SU2 will look almost like in this case, where we should be able to do it with paper and pencil. Again, if you don't trust me in this talk, if I go too fast, just do it on your own piece of paper after. And for SU2, the answer will be just like for U1 divided by extra Z2. So that's very often, because the group is larger, but gauge group in physics is not really a luxury. It's a symmetry by which we have to divide. So gauge invariant objects here and here are actually very simple. Again, modulo, that's it. So One question to which I wish there was a clear answer 10 years ago when I went into sort of this direction, trying to compactify theories from 6 dimensions to lower dimensions, is something like this. So let's take the even low enough dimension, n equals 2 for now, and take the simplest 2 manifold, or one of the simplest, the 2 torus. So 2 torus has a flat metric, so we don't break any supersymmetry. And those theories we start with that are maximally supersymmetric. So we kind of guarantee to land in maximally supersymmetric world in 4 dimensions. Moreover, so yeah, maximally supersymmetric theory. Moreover, it will have SL2Z symmetry, which is associated with the symmetry of reparametrization of a 2 torus. And that perfectly fits as duality group of maximally supersymmetric Lagrangian theory that we know for dn equals 4 superemits. So one natural question is, should maximally supersymmetric theory in 4 dimensions be unique with S duality and all the bells and whistles? So therefore, are they the same? And when I was young, expectation was the answer is yes, and nobody even questioned this. Surprisingly, modern answer is no. And they're not the same, and we have to pay attention to details, and this is kind of first thing that we encounter. So one of the easiest way to see this, which is kind of slick, and you may be left after the slide with the feeling that I'm cheating, so that's why we go to the next slide and we don't go further and further, is that the original 6-dimensional theory with which we started has 2 form so-called center symmetry, and that's why I call it C on the slide. And C can be the center of the original group that we chose to work with. So U1 is a billion group, so its center is itself, so it commutes with everything. In SU2, the center would be Z2. It happens to coincide with that wild group I mentioned. That's different Z2, but same in this particular case. So there is a 2-form, just like we had the 2-form B, there is a 2-form symmetry in the original theory in 6 dimensions. And our job is to reduce it down to whatever the lower dimensional theory is. So in particular, once we have a 2 torus or any other manifold, we have to decompose all our fields, as Caltech told us, into various differential forms, harmonic forms on this manifold, and they'll give us low dimensional spectrum. So that's basically what we have to do. So 2 torus has various homology groups which measure how many cycles of different dimension you have. And on a 2 torus, you have 1 0-dimensional cycle, it's a point. You have 2 circles. You can think about it as 2 non-trivial circles on a torus, sometimes called A and B cycles. And you have the volume form, which is the torus itself. So therefore, you have this kind of structure. And the composition of the symmetry, basically along the cycles of this 2 torus, physicists sometimes say that you take this form and it traps various legs along the directions of the torus. So for example, we can take this whole 2 form and integrate it entirely on a 2 torus, basically make it proportional to the volume form. Then in the resulting 4 dimensions, we'll get a 0-form symmetry, which will be the same C that we started, just changes the degree. So we'll get 2 1-form symmetries and 1 2-form symmetry. It basically follows the Hodge decomposition. Now, the issue is that 4dn equals 4 superemils has only this 2 and not this 2. And then there are various delicate questions related to choices of polarization and other details, but they're not going to help us resolve this issue because we see that symmetries just don't match.
Is there a Lagrangian for this thing?
Yeah, so I'm very careful about definition. So for dn equals 4, of course, yes. But for this, that's the question. So is there a Lagrangian? Not that I know of. At least not in a form that we can work with. And that's going to be an issue. In fact, as we increase dimension of this manifold that we compactify on, or if it has more interesting topology, like more and more of the cycles, things will get worse and worse. It will be harder and harder to answer this question. Yes, please.
So since these are CFTs, is there anything known from the bootstrap about these fields?
That's a good question. Can you hold it for a couple of slides? Because then it will be, it's almost, so the best answer I can say, so I had it on the previous slide that, oh, this is a CFT because it's meant to be a fixed point. the answer is a little bit more delicate in a sense that the way these theories are defined is that you take our six-dimensional theories on some manifold and manifold of a finite size. And then instead of allowing RG flows and other things, we basically, the way the definition works is we do topological twist, partial topological twist. That's where supersymmetry is important along this manifold. So we kind of freeze the dynamics along these internal dimensions of MN. And because of this, the question is very delicate. It's so the answer to both of the previous questions would be yes, resounding yes, if I allow the size of this manifold to go to 0. Or if it's very large, we basically decompactify. But I'm kind of stuck because of this topological twist in the intermediate region. And I'm asking, what's there? And that's very confusing because the best I can answer your question, which is very good, it's basically right to the heart of the story. I won't have the answer until the end of the talk, unfortunately. It looks like it's not a single CFT, it's more like a collection of CFTs. So that's the best answer I can give, and you'll see in a second why. So that's why I'm saying, let's get back to it in a few slides. Don't have. And again, I only know aspects of this story, so I'd appreciate input, or again, if this talk inspires you to think more about these questions, that's great. So then it has more questions than answers. And this is one.
Can you define a scattering amplitude for this thing?
For that, I need to have clear notion of states.
Yes.
That is scatter, and we have access to some of them, but very limited. That's yeah, same issue.
Well, what do you mean by some of them?
For example, highly symmetric. So these theories have symmetries, and if a state is highly symmetric or even supersymmetric, including that in the symmetry, then we can say something. But otherwise, I don't even know the spectrum in most cases. That's the issue. So this is like, again, whole class of theories. There are tons of them because we can choose any manifold you like up to dimension 6. So there are zillions of them, like grains of sand on a beach or stars in the sky. And then for most of them, we have no idea what the theory is. That's the real problem. Very sad. Okay, what about this argument? I mean, is it okay?
What happens for U1? What happens for the U1 case? Everything works, the 2 form and the 0 form.
No, same thing, same issue. I mean, in one case, this would be a billion, so it's a Maxwell theory, but same thing. Maxwell theory has these symmetries, but it doesn't have any of this. So we just shrug. Something's wrong. So this quickly shows that the answer is no, so they cannot be equal. But okay, so we can dive a little deeper, like what's going on. So what's happening?
Can I ask, is there an easy way to see why it's a 2 form symmetry, not a 1? Because usually the center symmetry is a 1 form, right?
Well, yes, but it depends on your original gauge symmetry that you start with. So here, remember the D field on some of the previous slides was already a 2 form, and that's why this is a 2 form.
But B is gauge invariant, so is it not?
No, B is not gauge invariant, but that's why it originates as a center symmetry that commutes.
So these fields here are all charged under the U1 equation.
Yes. So all of these fields that I listed are charged. Well, under U1 they're not really, because again it's meant to be adjoint. So in U1 case it happens that adjoint is.
So it's a gauge invariant then.
This fields, yes, but B itself is, I mean, it's a gauge connection.
It's a connection.
For that same. Right. Other question.
So because you're doing this topological twist on the base manifold, is the resulting theory unitary or not?
Yeah, it's partial topological twist. So it breaks some of the symmetries of the original theory, but it preserves. So the resulting theory should be unitary, should have some degree of supersymmetry, and so on and so forth. There is nothing. I mean, it should, in many ways, it should be like many theories we know and love. In fact, it should have many good properties.
Is your question about the situation where maybe you sort of said this, but is it a question about the limit when the torus trends to 0 side, or are you keeping the torus sort of finite?
It's finite. So that's why I mentioned the topological twist, because that's like a freeze card that tells me, okay, freeze the size of the torus.
So the moduli space will not quite be here. what we're used to.
Exactly, and that's where I wanted to discuss this collection of theories, and one of the next slides. That's it, actually. Okay, so since we encountered this issue, I'll quickly go over this. Like I already mentioned, the problem will become more pronounced as we increase the dimension n of our manifold in which we compactify. For example, we can consider the whole family of n-dimensional tori, Tn, and use that as our family for different n. So then you can ask, why did I skip n equals 1? N equals 1 is interesting in its own right, and it's kind of subtle. So in fact, even here, there are some potential issues. So if I start in 6D and follow what Caltech and Klein did, I'm supposed to take my 6D to form B, and whether I wrap one of its legs on a circle, in this case, this is just a circle or not, because it's self-dual, I get gauge connection 5 dimensions plus other modes. For scalars, nothing happens. These are just zero forms, so there is no interesting stuff going on, except that I'll have a whole bunch of KK modes parameterized by momentum on a circle, and the same for fermions. Okay? So then non-trivial question is, what is this theory, T of S1? So one can ask, again, it's maximally supersymmetric. Is it just maximally supersymmetric 5D superannuals with the same gauge group? And the answer is, I mean, it's very murky, and I honestly, I don't know the answer even up to present day. So I think kind of belief is yes, but there are quite a few issues or holes to fill, and many people wrote good papers about it. I'll try to go away from this question, but I want to mention it in passing. Because 5D superannuals is basically zero mode sector in this KK decomposition. And Caltech modes, parameterized by this momenta around the circle, they're not in the spectrum of 5D superannuals. So the question is, what are they? So some people would say, oh, well, we have to include instance-on sectors and so on and so forth. But I just told you in the abelian case, when our theory is free, the starting point in 6 dimensions was free, and the resulting theory would be 5D super Maxwell theory. So then how do you find this whole tower of fermions labeled by M in 5D super Maxwell theory? I have no idea. So I asked many people. There are many different answers I can share after the talk, and I would be glad if you share your thoughts. But this is tricky, and I don't, again, unlike other questions, I don't know the answer to this. I think the jury is kind of still out there. Many people thought about it, and I'm sure the answer. So one point I want to make is that here it's a little bit murky, but it's a little closer to yes than in other cases. But if you increase n, the answer will be no in a more and more glaring form. And in some sense, it will be easier to see the discrepancy. But whether it completely goes away or a question still remains in smallest value of n, I don't know.
Is the issue with Berlin that it's not renormalizable, or?
No, the issue is that, for example, we have a bunch of fermions parameterized by integers, right? So these are obvious KK modes. So the question is, what are they?
But in general, we're not talking about. In any of these cases, you want to capture the full KK type.
Yeah.
But that's not a 5-dimensional field anymore. That's a 6-dimensional field.
Well, it's 5-dimensional theory with a bunch of fields. So
like the reduced theory is always the theory of the KK, the zero mode zone, not the KK mode. The KK modes are never part of the reduced theory.
Well, no, that's an important point. I think here the definition is that we're supposed to capture all of the effective physics, or at least be able to describe like part of the tower.
But that's not a 5D theory.
Well,
many fields, it's not there.
no, I think right. So, but one answer that I can offer, just again, I don't want to go in this particular case in the woods. I mean, later we'll see that why these KK modes are important and why I want to keep them beyond just the zero level. They change things sometimes. But even here, so one answer could be that, oh, we should include in non-abelian case instantons. Then the question remains, how do you get fermions? So this n would be instanton number. So in fact, many people would argue that you should include instanton sectors in your theory. So that's again a question about non-perturbative definition. So some people would disagree. They would say, no, we should include all instanton sectors. That's exactly this integer m. But then I have to find some fermion modes in instanton sector n. In non-abelian theory, again, I believe this could be done, but in abelian theory, this looks a contradiction. I'll make it a little further. So some people would say we have to add it by hand. So that's kind of how these conversations usually go.
But in the free case, this power of space decouples, right? This has to be-
Right. So, well, nothing interacts, but they're still there. And in non-abelian case, we'll see that when they interact, it's actually not helpful. They change things. So we have to account for some.
You can do the linkage with this like small non-commutativity.
Exactly. So that's another answer that people get. So my complaint was there are no instantons in the abelian case. Some people say we have to add limiting cases. This is kind of called sometimes compactification divisors. If you think about space of fields, some limiting configurations in this case would be point-like instantons or non-commutative instantons. But then nobody, as far as I know, and there is a whole literature here exhibited this psi m literally as some fermion mode coupled to that non-commutative instanton. And again, it's murky. My point is, I don't want to debate this question, but as n increases, we will see in more and more transparent way, just like we saw with the generalized symmetry, that there is an issue, that something is off. That's the point. So if we increase either n or topology of the manifold, both lead to this. Okay, so coming back to here, a couple of other things that that are interesting and worth pointing out. So we can actually look at other symmetries, and many of these things I'm going to say will align in a second. So some of you said, well, let's not worry about high modes, let's just look at zero modes, right? So zero modes, after all, is what we're instructed to do, but again, actually other modes are also relevant. They're massive, so that's fine. Their effect is suppressed for low energy physics, but the fact is still there, and question is what it is. Sometimes it's going to be significant. But even at the level of zero mode, something is off. So for instance, if I take this theory, it doesn't matter whether I take this one or this one, and reduce it on another circle to get my two torus. So nobody objects that in the previous case we had gauge connection, right? So as part of the spectrum. So I'll have a KK mode of that gauge connection wrapped on a second circle, and that's going to be a group valued field. Okay. So therefore, if I'm following what Carlos and Klein told me, I'll find from this T of T2 that reduction of a 5D gauge connection on second circle will give me some phi, which is not the algebra value, but group value. And if I do that, it actually explains this symmetries and other things that we found. So some of the 0, 2, and 2 form symmetries are related to this fact, and that's about zero modes. It has nothing to do with KK modes. And only one of the scalars in this 4D T of T2 theory will be group value, but the other 5 guys will be the same scalars as we started with. They are Lie algebra value. So the theory will actually have same SO5 symmetry, not SO6 symmetry. That's another smoking gun and distinction from 4D n equals 4 superunits. Okay? So something is interesting happening. And the more you dig, the more you find that, okay, there are this little disconnects, but they kind of fit together. In particular, as some of you anticipated, and I want to invite you to explore the moduli space, the Coulomb branch of this theory. So many people have studied Coulomb branches of 4D n equals 2 and n equals 4 supersymmetric theories in 4 dimensions. And for example, with gauge group with SU2, the famous picture, which is sometimes called Cyber-Clayton plane or U-plane, looks like this. You have one complex variable parameterizing the base, that's the SU2 case, and there is elliptic curve fibered over this plane with one singular point, some interesting singularity, such that monodromy in basis of cycles of this torus is -1. So if you actually try to reproduce what the answer for T of T2 should be, you can, first of all, convince yourself that very quickly from general abstract reasons that you would expect monodromy +1, first of all. And then if you follow the argument, you would actually get something which looks like a cylinder. At least that's going to be exactly the answer in U1 case, because In U1 case, all we have to do is to combine this group value scalar, which is for U1, the group is U1, so it's a periodic scalar, with some other scalar, and you get the cylinder, which goes into plus infinity, minus infinity. It's like a long tube. What happens in SU2 case, this is an exercise. I'm not going to explain in detail, but as I mentioned before, very often for SU2, the answer is the same. You just divide by Z2. And the moduli space, this Coulomb branch, is just quotient of the cylinder by Z2. And it actually has two singular fixed points here in the corner. So you think about it as like, I take a tube and pinch it somewhere in the middle, and I'll keep only half. And then there are two corners here that I created that are singular. And each one is actually exactly of the same type as 4D n equals 4 superangles. So this theory, T of T2, has Coulomb branch, which has two copies of 4D n equals 4 superangles, usual Lagrangian conformal theories, glued together in a single bigger modulus. Actually, this is something that brought me to Thomas many years ago, and we started discussing this. And this phenomenon is kind of underlying many of the things that go on in this compactification. And again, moduli space is typically a question about zero modes. It's not even about KK modes. And as you can see, moduli space can be different. And in fact, the fact that this asymptotic region looks like a circle, and I can rotate it by pi, is exactly related to those symmetries that we don't see in 4D n equals 4 superangles and so on. So this picture actually explains many of the facts I mentioned before. All right, again, I hope that it illustrates that, well, the facts that we're discussing are delicate. Once we go to low dimension and increase the dimension of compactification manifold, the distinction kind of grows, and we see more and more differences. Any questions? Okay, that's exactly what I'm going to do next on this slide. So if I increase my dimension n, or TTN, n-dimensional torus on which we compactify and go now to T of T3. So my internal manifold is a three-dimensional torus. Now I have three circles. My effective two-dimensional theory is going to be of dimension 6 minus 3, which also happens to be 3, so some three-dimensional theory. It's again maximally supersymmetric because tori don't break supersymmetries. And maximally supersymmetric theories in 3 dimensions are typically known to be ABGM type theories, so we get them. But now we get many of them. Like I say, this distinction, this phenomenon that we saw in previous slides now proliferates very quickly. So for instance, in a abelian case, it's very easy to do the reduction. We start seeing that we have 3 cycles of the torus, so we have 3 momenta along basic directions of the torus labeled by 3 integers. So by following reduction from previous case, again, keep the group abelian, for instance, you see that you get gauge connection of type G. You have 2 group value scalars. And since we're in 3 dimensions, for example, if G is equal to U1, you can actually dualize the gauge field also in a compact scalar, so you get 3 compact scalars. So the moduli space will have 3 circles, S1, and if you write the full moduli space, it will be something like C star cross C star cross C star, 3 copies. So C star is a cylinder of the type that I described before, cross C. So this is like the algebra value. But group valued fields appear 3 times. And for SU2, again, answer is the same. If you follow through arguments, it's the same divided by Z2. So now, each time there is a fixed point of Z2 action, there is a singularity, and you can quickly see that there are 8 of them, 2 times 2 times 2. So there are 8 APGM singularities in this big moduli space. So in this case, T of T3 looks like 8 copies of APGM glued together. Okay. So
they're identical?
Huh?
Or identical?
Well, they're internal. I mean, each individual one is the same as everybody else, but they're positioned in this atomic molecule-like structure. So they interact through some of the modes on this Coulomb branch or modulus.
They're related by symmetries, right? Related by
That's right. So they're related by exactly this 0 form and 2 form symmetries we were discussing before, something that was missing in just single copy becomes very relevant and permutes different contexts. That's right. So those center symmetries that we discussed, that they can be explained through this picture, and in particular, they permute different theories. That's right.
As in this case, it turn on flags on the three tors for the center symmetry. Is that compatible with symmetry or is it not?
That's a good question. I think you can. Right, but what's the effect of that flags? I'm trying to think. Okay, I'm not ready to commit. That's a good question. I'm not ready to commit to what the effect is going to be immediately. That's a good question. In any case, we're discussing without the flags. Right. So yeah, that's the illustration, and okay. Again, it's good to be suspicious and ask, like, okay, what's going on? So we're kind of discussing maximally supersymmetric theories. Sometimes people say they're like unique. So what's the deal here? Is it even legitimate to consider such theories? I mean, how shall we think about? So, for example, the question is it a CFT or a collection of CFTs? I quickly run into out of standard arguments or tools when I try to ask or answer these questions. So I think they're good to consider. But I also want to point out that they're not totally esoteric, because it's meaningful. I mean, for example, can we see this 8 somewhere else? Okay, and here we compactify this 6-dimensional theory on a 3 torus. So we can ask, what is the corresponding Hilbert space, for instance? And we can compare that to Hilbert space of 4D n equals 4 super Mills on a 3 torus in SU2 case. So this picture is for SU2. And if we do, again, the answer is going to be different for this T of T2 versus for D n equals 4, but the answers will be related, and related in a very specific and concrete way. In particular, in such a way that even all these 8 copies, they're actually relevant to the answer. So if you do calculation for 3 torus and 4D n equals 4 theory, we'll see that the answer for SU2 is equal to 10. Okay, and this 10, again, if you go through it, it's basically going to boil to the same picture and will be equal to 8 plus 1 plus 1. Okay, so you can kind of see the same 8. So for 3 torus. And what happens if you ask the same question for this T of T2 starting in 6 dimensions? Instead of 10, the answer will be multiplied by 2. That's the same C2 that we saw every time we add a direction or circle, and it becomes 20. But mathematicians also consider this question in slightly different context. So they have this esoteric notion of scale modules as an invariance of 3 manifolds and 4 manifolds. And for them, the answer is actually 9. But and it differs. So 9 here is 8 plus 1. So it differs in how many ones we have, but both agree in terms of 8. So these 8 points are definitely present as a main contribution here and a main contribution here. So again, we could try to argue that maybe we should not worry about this moduli space theories connected to each other, but it's actually a good thing. So it's useful, and it appears in other contexts. So definitely we want to keep it. So we want to understand it. So maybe I'll go through next slides fairly quickly, because so there are 2 more parts to the talk, and this part is going to be kind of short. So if we compactify the 6D theories on a general 3 manifold, we land in 3 dimensions, and general 3-dimensional manifolds look like this, so they can be parametrized by this sort of complicated looking diagrams. That's why we have many, many different manifolds to choose from. And one question in this business always has been, like, can you describe find a Lagrangian for these theories? And many people tried. For example, this guy spent a lot of time, like most of his career, trying to address this question, and we don't know the answer. So these theories, parameterized by such structures, should look very much like quiver type theories, where each vertex is labeled by some integer, is adjoined 3D unequals to vector multiply with the Chern-Simons coupling, supersymmetric Chern-Simons, and that is exactly this integer label. Community has no concern about this part. But just like in our previous examples, concern is about the matter. And whether it's Lie algebra valued or group valued is going to be an issue. Because the tempting thing is to say that to an edge, we should associate some kind of matter. You can have two gauge groups, maybe it should be bifundamental, so that's like very natural. But the problem is, and that's probably on the right track, but the problem is that it should be group valued, not Lie algebra valued. Otherwise, we just don't get symmetries working, as in previous cases. And we thought about it, for example, in this paper with this young people, and the best we could come up with is that it should be some kind of, this edge, this matter in this theory, if it exists, a Lagrangian description for it, it should be some kind of like nonlinear sigma model, very much like Skerny model that Tony Skerny used to describe quarks and nuclear physics. So this is where you allow some of the fields in your theory to be group valued. And I think a lot of this work would benefit by developing the physics and fixed points and understanding of theories where we take matter fields to be valued in groups rather than Lie algebra. So that's one lesson we kind of learned from that KK reduction. So they look similar. So if you take group and approximate near origin or near point, some special point, of course, it looks very much like Lie algebra, but then they deviate. For example, in SU2 case, the whole group is a three-dimensional sphere, and it looks like a three-dimensional plane on a very small patch. That's the Lie algebra, but global structure is different, and it's exactly this global structure that leads to this generalized symmetries and other things that were causing us trouble with modulus. Okay, so another application that of this kind of analysis that we saw is that this theory of T of T2 versus 4D unequal 4 superreals, as we concluded, are not the same. And indeed, actually, we ran into this issue much earlier. In fact, that's how some of this work has started, because one can consider that for the theory on a 4-manifold, sort of kind of combined T2 cross a 4-manifold compactification, and depending on which order you follow, we run into contradiction. So if you follow 4D unequals 4 superreals on a general 4-manifold, you would learn that your partition function should be some interesting invariant, namely modular form of a given weight, which is determined by 4-manifold. But if you follow this T of T2 and compute from 6D anomalies what the modular weight should be, you would get a very different answer. And at first we thought that, oh, this is maybe a minor mistake. For example, here it would be minus for the characteristic of a 4-manifold divided by 2. Here it's a plus. So maybe we thought, oh, maybe it's a sign mistake. But then there is another term related to the signature of the 4-manifold, which was absent. So it was kind of strange. In fact, later, after spending a lot of time trying to fix what the right sign should be, we realized that, yes, this is actually better because the difference between them is a better object mathematically. And again, in this case, you can understand that these two are not the same, and that's actually good news because you could say you have more theories or more invariants of manifolds this way. And part of the story is that indeed, one of the fields that's relevant for this story should be group valued rather than Lie algebra valued. But this is a good illustration where not only zero modes should be different, but in fact, to explain the signature where it comes from, you actually have to keep the whole tower of Caltech modes. So this is a kind of effect that if you're careful about these KK modes that we're debating that they should be included or not, if you include them, and then there are infinitely many of them, they're massive. So it's kind of interesting situation. Usually we say that massive modes should not affect low energy physics. So effect should be kind of zero. On the other hand, if there are infinitely many of them, we get 0 times infinity sort of situation. And that's exactly what's happening here. So if we regularize the contribution of this infinite tower of modes, we actually get exactly this term. So, and then everything aligns, we're happy, but it takes a while to realize that, yes, it's exactly the contribution of people. Okay, in the remaining 15 minutes, I want to switch gears and talk about approach the same elephant from another side. So in various fields, including financial markets, there are these terms or events called black swans. And I think it was mainly popularized by Nassim Taleb and others. And what this refers to is that actually until fairly recently in the history of our world, it was believed that all swans are black. Until they were found in Australia 100 years or a couple 100 years ago, I don't remember. Oh yeah, here. So this Wikipedia page tells me. But now they're used as something that unless you see it, you suspect that there are no such things. Namely, it describes phenomena that are not expected, but once they're discovered, of course, you realize, okay, they should be included in consideration, and there is no reason not to. So they refer to something that's pretty rare, but once you discover it, it's there. So, for example, stock markets crashes are of the same type. So they happen rarely, but these are very rare events with fairly large significance. You don't want to kind of ignore them. And conclusion about the color of swans, it's a significant conclusion. So you have to discover just one and maybe pretty far, but once you discover, you change the whole paradigm. So that's what's going to happen to us next. And I want to talk about this so-called resurgent analysis. Could be, again, if you haven't seen it before, so this is kind of summary slide from high-level picture. It's a very useful computational tool. So it's not just about symmetries. It allows you to compute details about scattering amplitudes or other delicate quantities. So it's very computationally, intense, strong. Maybe that's the right word. And people sometimes view it just as such, but here in this talk, I also want to emphasize that it actually brings interesting qualitative lessons as well, beside quantitative computational power. And this part is based on some papers mentioned here, including the one with this young person who is currently on the job market, and he's amazing. So in a nutshell, what resurgent analysis does, it takes space of fields that we understand or don't understand, and allows you to project everything to a complex plane called Borel plane in the subject. And this complex plane is meant to be like a photograph. So it captures interesting information about physics. It's like fingerprints or photographs, some partial information, which actually in many cases is surprisingly rich. So typical way it works is that it allows to get interesting insights into non-perturbative completion of the physics, and that has been the theme of the entire talk. Where you start with perturbative answer, you try to resum it and draw the answer on a Borel plane. So resulting plane looks kind of like this. We care about singularity structure on this plane, and then you're supposed to infer non-perturbative physics. So at the level of formula, you have some perturbative series. You do very specific mathematical operations. It's almost like a cookbook, so you can follow it. In fact, you can really write code for forming the steps. And the output is supposed to be insight into non-perturbative physics. All we have to know is that this Borel plane basically captures interesting information about both perturbative and non-perturbative physics. And also singularities on the Borel plane are classical saddle points, classical solutions to the system, or some instanton solutions. Which instantons are kind of this peculiar configurations that could be viewed as totally classical, but at the same time, they provide a window into a non-perturbative completion. So Borel plane is the same. It's one-dimensional complex plane, and we can use lots of tools from analysis to analyze this, and people are super excited about it. In particular, it could help us answer the following question, which is the last question for the talk that I want to pose. If you have a Q of t and it's defined perturbatively, can I expand that non-perturbative completion of this Q of t necessarily needs to be in a larger theory, or it can be done with the degrees of freedom of what I already have on the table? Okay. And we of course know two types of answers to this question. There are some theories that require additional degrees of freedom and need to be embedded in something larger. And typically, for example, some theories need to be embedded in string theory from such, and some are totally fine on their own as non-perturbative objects we can work with. For example, for Dn equals 4 squaring meals, Lagrangian theory is kind of like. So from the resurgence analysis, how could we answer this question? So people who study resurgent analysis, the main object for them, as I said, is this Borel plane, the complex plane, and they like to use identify singularities on this plane, and they identify classical solutions or typical category. So in fact, this is the picture that some of my collaborators from the field in mathematical physics or math like to use. They I guess romantically associate Borel plane with this level of surface of water, where this water droplets indicate singularities that are precisely the classical action. So one way it could help, this whole theory could help to answer this question, whether our theory is Lagrangian, whether it requires something else as non-perturbative completion, is the following. Suppose we take our theory, and suppose we have only non-perturbative theory. If the study is Borel plane, if it includes singularities which did not belong to it, namely, which cannot be explained as classical solutions in the original theory, that's a smoking gun. That's an indication that something bigger is needed. That's a very concrete tool. In fact, that's how we can start using. So I would call this black swans, because you don't expect such singularities that correspond to, this Borel plane is meant to be complexified plane of your action, in the sense of Lagrangian and action in your theory. And if values of the action, the singularities that you see, are not action of classical solutions in the original theory, these are black swans. This is something we don't expect naively. But if they appear, that's totally fine. So then we need to realize that, okay, our theory is larger. So in other words, the question is, are these equal, or it's a strict embedding in something larger and larger?
Next question.
Yeah.
Can you see the singularities if you have infinitely many terms in the perturbative expansion?
Yes, that's exactly where everyone, I'm not an expert on resurgence. I recently learned it from colleagues, but that's exactly how they use this tool. So they have 20 terms in perturbative expansion, and this powerful technology is so powerful that it allows you to see, of course, approximation to Borel plane. So then instead of like exact singularity, you have a very sharp peak. And they literally use this picture is that outline for it. Right. So in my case, some of the issues with this theory is that like T of M, they rise precisely from the situations where the field space is non-compact. So, for example, typically what happens is that you have a gauge connection, and then it sort of effectively gets complexified by combining it with some scalar, a joint scalar. And the delicate point is that the space of fields, either infinite dimensional or at the level of moduli space, has this infinities. And we don't know sometimes what to say about if we go in this phi direction very far, 5 megaparsecs. I mean, shall we add something or not? And what often happens, especially if theory is embedded in string theory, like this T of M guys, there is indeed more life, and these are called compactification divisors in the field space or in the moduli space, and there could be some critical points hiding in these infinities. So these are going to be my black swans. Okay. So what's interesting is that in this case of T of M3 theories, until recently, we didn't actually see any reason for such singularities by analyzing Borel plane. But very recently, again, it's one of these phenomena. Once you discover it, you realize there are many, and it's easy to identify more and more examples. We and other people found that, yes, there are actually such black swans, namely singularities that don't correspond to classical solutions, as you expect. So indeed, there are these compactification divisors, which in view of this talk is not too surprising, because that's exactly the distinction between, say, Lie algebra valued fields and group valued fields, because in Lie algebra, you can walk all the way to infinity and never stop. But if your fields are group valued, they're trying to be more compact and curved and so on. And these are exactly this compactification divisors. Let's see. So my point here is that, yeah, so this Borel plane is very nice and useful tool in resurgent analysis, and it allows you very often to see very rich life that's hiding under the surface. So given the time, I think this is maybe a good place to stop. I'm happy to answer questions.
Say a little bit more about what's the nature of these compactification divisors, like. So, for example, yes, in the n equals 4 example, we have 2 0 theory and torus, which I actually know pretty well from some more paper that there are some cases where you get like unexpected singular points where you have some close-inclined particles becoming massless in a way that isn't necessarily expected from symmetries. Is that the kind of thing that you have in mind?
Well, in that case, it's adding degrees of freedom associated to the second, for example, if we work with SU2 gauge group, to the second for the n equals 4. So basically, it's always a partial compactification of either moduli space or space of field. So I can go pretty far back in the slides.
But in the SU2 example, you had all these guys were basically related by symmetry, so there was nothing unexpected. The moment you know that you have the compact direction and symmetry, you can predict the physics of any of these other points. Right. There are other examples for different gauge groups where you get unexpected such points that are not related by any symmetries and that have different physics.
Right. So if gauge group is bigger, right. So here to answer your question, for example, analog of compactification divisor would be complement of this small neighborhood of just one corner, which describes for the n equals 4. Everything else is in some sense compactification divisor, and it's directly coming from the fact that some fields are group values. But you're absolutely right that here I have the luxury of symmetry because I try to preserve it. But in other cases, so for more complicated manifolds, there may not be a symmetry. And that's where it was very hard to control these things. And again, resurgence is a pretty good tool. But if you try to naively follow what people have tried, like here, and describe effective physics using group valued fields rather than Lie algebra, then again, quantitative results are difficult, but qualitative results like symmetries, they naturally follow. So my point is that in many of these cases, so there are two kind of concrete points I want to make about physics. One is group valued fields, and the other is KK modes. And in some cases, group valued fields already explain that some partial compactification of space of field should be expected and should be irrelevant. But for some other delicate points, like for example, this anomalies, for instance, even contribution of KK modes is important. So these are two basic messages.
Is there any sense which you have an expectation for whether these link theories will give you sort of new, intrinsically different, strongly coupled fixed points, or could it be that they're just strongly coupled because you're patching together some known strongly coupled fixed points along some circle direction or something like that? So, for example, you didn't discover any strongly coupled n equals 4 theory. You just discovered that your example had kind of multiple copies of the same theory.
Right. So that's a very good question. I don't know. That's why I think partly people don't like term non-Lagrangian, because it's non-Lagrangian until Lagrangian is discovered or some useful description is discovered. So I don't worry about this kind of question because, for instance, here there should be some dualities which are very similar to Gideon-Kutasev and Aharoni dualities for these theories, where you're allowed to do certain moves and relations between this vertices. For example, you can change number of these vertices by changing the numbers, but from description of such manifolds, we know that there should be an equivalence, but in physics we don't know such a duality. So one obvious benefit of identifying what exactly this link is, even if it's Lagrangian, that's great, we'll discover a new duality that way. But this hasn't happened. So that's I think great problem to work on.
Thanks, Sergei, again.
Oh,